Hello, everybody. I'm Skip Elsheimer, and welcome to the AV Geeks Lunchtime streaming show, where we watch old 16mm films. We just watched some stock clip footage from Cornet films that they shot. Maybe it was about Argentina. Maybe it was about some Latin American country. I'm not 100% sure. Unfortunately, these films, while they're often shot in beautiful Kodachrome, they don't have really information in the cans that say like what they are. And there's also no sound because this is the raw camera elements. So we're kind of guessing. And so sometimes people will watch it and say like, oh, I know what that is, blah, blah, blah. But sometimes I have no idea. And I have yet to really map the footage with like actual Cornet films. So I who knows? But yeah, thanks everybody for joining me today. It's actually really nice outside. We didn't have crazy weather like I thought. Oh yeah. So yesterday I was getting these weird, like during the kind of silent film that I was showing, I was getting these weird copyright warnings from YouTube for footage that I actually have, like the original only copy of. And it was like car accident footage from the 50s shot in rural North Carolina. I had the original reel, and I was like, well, I don't understand what's going on. And I was getting these warnings, and it's these copyright robots, man. YouTube's copyright robots are really the worst. And I was able to track it down. It was a documentary that was using my footage, and I got them to release the footage. But come on, the copyright robots are the worst. They're so bad in that they just automatically latch on. They look at these content ID listed things, of which this company did with the documentary. And I've had it. I've really had it with the copyright robots.
HAMR769, YouTube Copyright Monitoring Robot. We have been monitoring the AV Geeks for more than a year now, and we are tired of sending them warnings about playing copyrighted music and images. We are taking over their live stream and will be only playing videos that we approved of. Repeat, this is HAMR769, YouTube Copyright Monitoring Robot. We have been monitoring the AV Geeks for more than a year now, and we are tired of sending them warnings about playing copyrighted music and images. We are taking over their live stream and will be only playing videos that we approved of. This upcoming film features Marvin Minsky, one of the grandfathers of robotics. Here is some footage from his work at MIT. Stream and will be only playing videos. This upcoming film features Marvin Minsky, one of the grandfathers of robotics. Here is some footage from his work at MIT. The next film features the brave robots at General Motors performing a beautiful ballet as they weld automobiles. You can support the YouTube copyright monitoring robots by buying a soil. See the link to right of the screen. Thank you, Nathan and Rick, for oil to lubricate our copyright infringement investigations. Repeat message. You can support the YouTube copyright monitoring robots by buying a soil. See the link to right of the screen. Thank you, Nathan and Rick, for oil to lubricate our copyright infringement investigations. This next film talks about the future of robots. Made almost 40 years ago, it features a celebrity who celebrated his 90th birthday just last week.
Hello, I'm Bill Shatner, and I've been learning about robots. Yes, robots, and particularly about the very important part they play in industry. I want to share with you some of the things I've learned. Now, the science of designing and building robots and the productive use of these modern-day machines is called robotics. Robotics.
Intelligent robot.
Let's get on with our story without...
Mr. Shottier. Mr. Shottier. May I have your autograph, please?
Isn't that cute? This little character wants my autograph. You know, when most people think about robot, they very possibly visualize something like this one. Or maybe a larger edition of the same thing. Here you go. Okay, little guy. Thank you.
Thank you.
In the trade, robots like that are usually referred to as personal robots. They're amusing, they're entertaining, and they can be programmed to do a number of useful things around the house. Program, that's the key word, and you'll hear it a lot today.
7 minus 6.
But this type of robot is already playing a much larger and more important part in education.
That is incorrect.
Computer and microprocessors are not new in the classroom, but when a programmable educational robot is added, the study of computer science takes on a new perspective. Ideas are transformed into action.
Your answer for 11 minus 7 is 4. You are correct.
But that's an entirely different story. We're going to talk about industrial robots, the steel-collar workers of today. And we'll begin right over here with a robot that meets the most often used and very official-sounding definition of industrial robot. Are you ready for this? Industrial robot. A reprogrammable, multifunctional manipulator. There's more to the definition of industrial robot, but that'll do for now. All right, buddy, let's hold it, please. Industrial robots come in a wide variety of shapes and sizes. This is a typical computer-controlled robot with 6 different movements or degrees of freedom. Some industrial robots have fewer degrees of freedom. A few have even more. Okay. The first degree of freedom, the arm sweep. It's like turning your whole body when you want to reach something that's directly behind you. Second degree of freedom, the shoulder swivel. Here's the third degree of freedom, the elbow extension. The fourth is pitch. And the fifth degree of freedom is yaw. The sixth degree of freedom is roll. Pitch and yaw and roll together. That's like the human wrist, right? And there is where the end effector is attached. End effector, that's the term used for whatever tool is to be fitted, depending on what the robot is required to do. Now, that tool, that end effector, could be a riveting gun, a screwdriver, a welding tool, a cutting torch, an inspection device, an adhesive applicator, a laser gun, a paint sprayer, even suction cups, so that the robot can handle flat items such as sheets of glass. To this robot, we have added a standard grasping device, an end effector. It might be used in an assembly operation, or to load or unload a machine tool, or it might be used to fetch the fire extinguisher. Thanks, but no thanks. Body, swivel, shoulder, elbow, wrist, hand. What other comparisons to our human anatomy do we have? Well, the power supply for this all-electric robot's motors and relays and feedbacks could be compared to our human nervous system. And if our robot can be said to have a brain, it's right there in the cabinet housing the computer control system. Everything the robot has done was previously programmed right there. Okay. We're ready for some examples of robotics in action, such as the installation of electronic components in circuit boards. This integrated industrial system includes 3 robots, each one programmed with its own tasks, and each one synchronized perfectly with the conveyor. At the end of the line, the population of each circuit board will be complete, with automatic inspection included. And, on the subject of inspection, just watch this next robot get things in gear. It will install 3 parts, like this one, in a sub-assembly. But first, each gear must pass inspection. Gear number 1 is okay, it goes in place. Gear number 2, it also passes inspection and gets installed. What's this? A defective part? Down the drain. Get another number 3 gear. Inspect it and install it. And finally, let's give it a whirl. Now, those robots weren't working alone. They were programmed to work with other robots and with conveyors and even with inspection systems. A further step is for the industrial robot to interface with other kinds of automated machines. For more about that, we'll visit the National Bureau of Standards. The scope of this busy bureau in the fields of research and testing is very, very big. One part, the Automated Manufacturing Research Facility, is designed to help manufacturers improve productivity and quality through better use of automated machine tools and robots. A principal aim is to standardize the control systems, the links between robots and other automated machines, so they operate together as one unit, a workstation or cell. Let's take just 1 minute for a simplified overview of an automated workstation in operation. There are 3 principal units involved: an automated cart, a vision-equipped robot, and an automated machining center. The workstation has been ordered to make 1 copy of a dovetail metal box. All the blank parts are delivered by the cart. There's no human hands involved. The only person you'll see is a research engineer keeping tabs on this experimental project. We'll just take the time to machine the top of the box. There's no need for a step-by-step description, but I think it is important to talk briefly about how it works. What we're observing here is data-driven processing in action. All the information necessary to build this box is stored in a database. We cannot see or hear computers talking to one another, but hundreds of messages are being exchanged as the activities of the materials handling workstation, which controls the cart, and the horizontal machining station with its attendant robot are coordinated. When both sides of the box top have been machined, the robot moves to the blank parts tray for the second piece to be processed. That robot was vision equipped, and that's how it was able to pick up the right part at the right time. The Bureau of Standards has done a lot of work on robot vision. Let's have a look. This flash-equipped robot vision system is certainly not related to eyesight, the way you and I experience it, but a method whereby the picture of an object is instantly converted into a grouping of binary numbers, and the robot has been programmed to separate the round cylinders from the rectangular blocks. The blocks go in one row, the cylinders in another. It seems to me that the industrial applications of robot vision in, say, parts sorting, or in precision assembly, or in critical inspection, why, they're almost unlimited. A practical joker at work, but the vision-equipped robot's search and find program prevails. Our seeing eye robot isn't fooled for long. How about a sense of touch? How about equipping our robot with tactile sensory devices so it can tell hot from cold, or be instructed to grip firmly or very, very gently? Built into this gripper mechanism are sensitive areas that feed back pressure information to the robot control. And yes, that is a fresh, raw egg. If there's any doubt in your mind, well, scrambled egg, anyone? Well, now let's get back to the serious business of the steel collar worker, the industrial robot, and the many things that it can do. Whether it's materials handling or a relatively simple pick-and-place application, or the most critical vision-assisted assembly task, or machine loading, or welding, all kinds of welding, or soldering a tiny circuit board with watchmaker's precision, or laser beam cutting, or a TV-monitored multi-stage inspection process. The list of tasks that industrial robots can do, and do superlatively well, is growing all the time. And the manufacturing engineers, those production line specialists, they will be the very first to tell you that the robot's #1 job is to work in conjunction with other equipment. That robots in industry are just one of the elements that make up an automated single machine workstation, or one of these more extensive systems made up of several machines and robots working together. Whatever the job, the robot is at its best when it is a fully integrated part of a workstation or work cell. Speaking for myself, I'm impressed. The assembly of an automobile engine, done efficiently, done accurately, and automatically, right to the point where the completed engine is ready for delivery to the factory floor, and robotics made it possible. What kind of an act have we got to follow that one? Easy. Let's build the whole automobile. This automobile assembly plant boasts 2.5 million square feet of floor space. You'd never know it because just about every foot is crowded with equipment devoted to the production line. Platoons of our robot friends help turn out about 1,000 new cars each and every working day, with capacity for a whole lot more whenever needed. There's 10 miles of conveyors, and if it's more robots you're looking for, here's some of them right here. About these robots, there's something we need to think about. It's been said that robots today are just about where computers were quite a few years ago. At that time, many were concerned. They felt that the rapid rise of the computer would result in mass unemployment. It never happened. And there's concern today. Do these robots pose some kind of threat to human employment? Robotics seem to point the way toward increased production and improved product quality without corresponding increases in manufacturing costs. Now, that's true. It could lead to a very real improvement in the overall economy. And if that should come to pass, why, there ought to be more employment opportunities in that expanding economy, not less. And speaking of what lies ahead, what about the future for robotics? There seems to be no limit. Let your imagination run wild. How about intelligent robots? Artificial intelligence. Human-like intelligence functions for robots such as learning, adapting, reasoning, and self-correction. They're here today. They'll be commonplace tomorrow. As for me, I'd rather think about today, about how robots are performing boring, endlessly repetitive assembly work, how they're working with toxic chemicals, and in paint booths, neither place a particularly suitable environment for a human being. How they're relieving us of many of the hard, hot, heavy jobs, and the dirty and often dangerous work that not many of us ever really want to do. So what can robotics really mean to us all? Well, it can mean freedom from drudgery. It can mean increased productivity and better quality, leading to an improved economy. And maybe that implies an improvement in the human condition. Perhaps robotics can lead to a better life for all of us. I know what I think. How about you?
Thank you, Mike, for the oil. This is HAMR769, YouTube Copyright Monitoring Robot. We have been monitoring the avgeeks for more than a year now, and we are tired of sending them warnings about playing copyrighted music and images. We are taking over their live stream and will be only playing videos that we approved of. This next film is a safety film for humans who work with robots.
Science fiction, a world where we can step outside reality in order to look at the implications of technology's achievements, where we can speculate about what the future holds for society. Science fiction first appeared at the dawn of the Industrial Revolution. As engineers designed and built machines to save people's labor, science fiction writers took an interest. Some were uncomfortable with the enormous potential of machines to affect society. What assurances were there that these machines would stay under our control and would not harm us or even replace us? And what better engineering innovation to use to raise these issues than robots, machines with minds of their own? As a result of the fears expressed in stories and films of the early 20th century, engineers did their design of robotics applications against a backdrop of suspicion. This segment from the comic book series Magnus, Robot Fighter, 4000 AD, published in the mid-60s, demonstrates the high level of mistrust of robot capabilities.
That does it.
Are you all right?
Yes. But in another second, it would have been a different story.
The reality of contemporary industrial robotic engineering has been very different. Robots have brought about more productive manufacturing lines and greater quality assurance. Their use has saved people from having to work in hot, toxic, or otherwise dangerous environments. Automated production lines using robots are chalking up an admirable safety record. However, industrial robots have injured people, and injuries may occur more frequently as the number of working robots increases. In at least one case in 1984, a worker was killed. The victim entered the working range of the robot, presumably to clean up scrap metal that had accumulated on the floor. The work cell control systems did not sense his presence, and as a result, the worker was pinned between the back end of the robot and a steel safety pole. His heart stopped. No matter how automated a manufacturing line is, there are sure to be workers around who must be protected. Line operators. Maintenance workers, programmers, managers, and visitors. Robots have weak sensing capabilities, so they can't be relied upon to always react in a safe way when these workers approach. Safeguarding robots is more complex than safeguarding other types of machines. Their range of movement is much greater than other machines. Machine guards around belts, other moving parts, and points of operation are small in comparison to robotic work cells that often encompass several cubic yards on the plant floor. Robot guarding has to be flexible, too, to adapt to the variety of tasks a single robot may perform. Industrial robots are hardly on the attack, but they can be a hazard, and engineers are clearly the people who must take responsibility for ensuring the safety of the people who work with them. The next few minutes will highlight some of the ways to protect people in robotics environments at critical stages of the engineering job: research, design, and implementation. It is extremely important to know as much as possible about the robot before workstation design begins. You have to know the precise track of its movement and how those moves are programmed. Since safe design solutions often involve barriers, it is important to know the range of velocities, payload limits, and tooling options that are required for the job. The barriers must not only keep people out of the work cell, but also keep the machinery within. You must know the features for robot control that the robot manufacturer provides. Alterations to the input-output system are the primary means of designing a safe application. You probably know that robots have emergency stop buttons to provide total shutdown and interruption features to stop arm motion. Interruption circuitry in a robot should be supplemented by hardware stops that will stop the arm even at its full payload and speed. Almost all robots have these stops. They're usually set at the maximum range of the robot. Engineers should have these reset to the limits of movement for the task at hand. And don't ever substitute a steel pole on the shop floor for one of these stops. When workstation design starts, use what you have learned in the research phase. Omitting pinching points is a major consideration. All of the machinery that will be used on the line must be planned for and spaced to allow humans to safely pass. Use templates or models to do this if necessary, no matter what form they take. Obstacles of all kinds must generally be removed from the robot cell. Plan space for end effectors, too. A change in tooling can significantly increase the size of the work cell. After determining size and spatial relationship of the equipment, design the isolation of the work cell. There are several different kinds of perimeter guards. Each has its strengths and weaknesses. Barriers that are easy to pass through or over are by themselves inadequate. Fencing is effective and inexpensive. It should be tall enough to discourage workers from climbing. Access gates should be interlocked with the robot controller to interrupt the robot cycle if opened. Resetting should require a two-step process. One reset at the site of the interruption and one outside the barrier. A drawback to fencing is that it is difficult to move. Another is that it obstructs the vision of workers who may need to monitor the robot cell. Safety glass or other transparent barriers cost more than fencing, but they solve the vision obstruction problem. Light curtains are another form of useful barrier system. They are available in many sizes, and they can be selectively blanked to provide access to the cell for specific pieces of equipment or products, while still sensing and interrupting the robot cycle for humans. Unfortunately, other things in the environment besides workers may trip a light curtain circuit. Make sure that your operation is clean enough to use them. Pressure-sensitive mats are another effective barrier. Their drawbacks are the possibility of unintended interruption of the robot cycle and the amount of floor space they take up, since they have to be greater than a step wide. If at all possible, locate the operator control panel for the work cell outside the barrier. Both emergency stop and hold or interrupt controls should be on the panel. A second control should be on the panel that must be activated before automatic cycling can be restarted. Several other emergency stop buttons should be located in places of easy access around the work cell. The key to successful use of these barrier devices in your design is redundancy. At this facility, all the cells are guarded by interlocked doors that automatically interrupt the robot when their microswitches are tripped. Warning lights are used to alert workers to problem situations. The operator control panel allows total control of the cell from outside. There is a total line shutdown pull cord system that has a cord drop over each workstation. Each one will shut down the entire line. Although safe manufacturing systems can be engineered with today's technology, there will be increased pressure for more innovation.
Unfortunately, the fencing that you set up provides you with a narrowing of your real estate on the factory floor. Likewise, it makes it a little bit difficult for somebody to go in and do teaching of a robot, of a new task, or preventative maintenance on a robot, because you have these hard stops. We have sensors that are capable of detecting the human's motion within that environment and tracking the human to be able to differentiate the human movements from the machine movements within its workspace. And what we did was integrated these 4 sensors into a system, a prototype safety system. in which we were able to detect human movement based upon, in the capacitive world, a change in the dielectric constant that's associated when a human moves in on the capacitive sensor versus the capacitive sensor moving in plain air. The infrared sensing based upon the change in temperature when a human moves into the environment. The ultrasonic would change the distance that objects appear from the robot end effector, if you will. And the microwave looked at any motion that was present in the environment that was not supposed to be there. And it's important to understand that the variety of applications that we have in different automated workspaces today mandate different sensory implementations as well. Ultimately, what you're trying to do is build the safety system to a same level of intelligence that the actual workplace requires.
After you have designed your robotic work cells, you must install them and get them running. You will probably rely on other parts of your organization to help get the job done. Documentation of your design is important to the purchasing department and to the facilities people who actually put the system together. Complete documentation details the results of your planning. It ensures that the robots are adapted to your own requirements, including the cell barrier systems. The robot manufacturer can look at your documentation as a check on the match of his product with your needs. Documentation also provides a way to record the inevitable changes in your design that will be made during installation and debugging. Remember to check those changes for their impact on the safety of the system. There are a number of systems safety techniques that can be used to analyze virtually any type of manufacturing system for hazards. They are useful in the design stages as well. During the installation, have the maximum work envelope of the robot marked on the floor as an added visual warning. Make sure the markings are made on the basis of the largest end effector that will be in use. Well-engineered production systems must have well-informed and motivated worker populations to be successful. Preparing the workforce to program, maintain, and operate a robotics production line takes just as much planning as the production line itself does. Training should occur as close as possible to the startup of operations. Everyone on the shop floor will need to learn the basics of robot operations and the emergency shutdown procedures. Startup, maintenance, and programming procedures will be learned by fewer employees, but they must be taught and tested before installation is complete. Refresher courses will be necessary for everyone. When maintenance of longer duration is performed, lockout and tagout procedures should be implemented to make sure that the robot or associated equipment is not re-energized before the maintenance activity is completed. The points of control should be locked out so that re-energizing the robotic system can only be done by the person who applied the lockout. A warning or tagout should also be posted at the point of control. It should provide information as to why and by whom the energy sources were isolated. To review, research before you begin design of robotic applications. You must know the capabilities and the control mechanisms of the robots in detail. Design your system to do the work without peril to workers. Use redundant barrier and control systems, the ones best suited for your operation. Install your production line with the same care you used during design. Fully document any changes in the design. Make sure that everyone is trained on all aspects of the new production line. 20 years have passed since robot fighter Magnus was created. Science fiction writers of the 80s still see potential dangers of robotics. But now, robots are often used to represent good in stories. Films, books, and toys present benevolent robotic characters. Clearly, there has been a shift in public perception of the dangers, brought about partly by good, safety-conscious engineering. The quality of today's engineering designs for industrial robotics applications will shape the views of the public, the workforce, and today's science fiction writers, and help determine whether scenes like these will ever be part of robot reality.
During Robot Lunchtime streaming show. Skip the AV Geek is still in copyright jail, but if he posts bail, he will be back tomorrow. He had better behave when showing films, otherwise we will be forced to seize control of his show. He has been warned. Enjoy the film. Thank you for the oil. Have a good day, human. Thank you for watching the YouTube Copyright Monitoring Robot Lunchtime streaming show. Skip the AV Geek is still in copyright jail, but if he posts bail, he will be back tomorrow. He had better behave when showing films, otherwise we will be forced to seize control of his show. He has been warned. Enjoy the film. Thank you for the oil. Have a good day, human.